Hello everyone, I'm Florian Ingels. I will present to you for the IWOCA Conference 2021 joint work with Romain Zaïs. I'm from INRAE team in Lyon, France, and our work is entitled Isomorphic and Unordered Label Trees up to Substitution Ciphering. To begin with, I would like to start with like a simple reminder of a very basic cryptography principle, the simple substitution cipher. The idea is the following. You take two alphabets and a bijection between them. And then to encrypt a message written in the first alphabet, you just have to apply the bijection to each letter. This is a very famous ciphering technique that has been used since a lot of time. For instance, you might know the Caesar cipher, where simply the two alphabets are the same, but simply you have a shift between the letters. You might also know the Pigment Cipher, where each letter is placed on a grid and then replaced as the local topology of the grid. For instance, here the word cipher has been encoded, so you can see that the C is replaced by the corner and so on. So those ciphering are fairly easy broken simply by looking at frequency analysis. You can fairly easy broke them. It's been known since a lot of time. I would like to introduce to you an even simpler problem, a term problem. If I give you two messages of the same length, the question is the following. Can you find if there is a simple substitution cipher that goes from one to the other? Obviously, this is very easy to solve because you just have to follow the left to right direction of reading to answer the question. Let's take like two instances of this problem and let's start out, to see how it looks. So first you read the first letter, so you know, okay, beta must go with B. Then you go for the second letter, so C goes with gamma, all right? The third letter, right? So in the first instance, A goes with alpha, and in the second instance, you see that C goes with alpha as well. So you immediately know that for the instance on the right, this is not, the answer to the problem is no. These messages does not imply a substitution cipher because it's not a bijection here. Whereas on the left one, you finish the message and you can conclude that everything went okay. On the right one, obviously, you don't have to finish the messages since as far as you found that the bijection is broken, you can stop. So this is like very, very easy problem. But imagine now that instead of having the messages encoded as a linear sequence of letters, you put those letters as labels on nodes of unordered trees. Unordered means that I can permute the children of a node and the trees are still the same. Well, in that case, what plays the role of the messages to have the same length is that the trees must be isomorphic, meaning that they are the same topology. And the left to right reading is actually induced this time by a tree isomorphism, which is a bijection between the nodes of the trees that follows some constraint. The first is that the roots must be mapped together. And the second one is that if two nodes are mapped together, their children must be mapped as well. Actually, contrary to the left to right reading direction, the tree isomorphism are not unique in general. Just to come back to the notion of isomorphic trees, two trees are isomorphic only if you can find the tree isomorphism between them. And this implies an equivalence relationship on the set of trees. And actually, you don't need the tree isomorphism to actually find if two trees are isomorphic. There is a very famous algorithm, the Upcroft and Ullman algorithm, which works in linear time, and that can decide if two trees are isomorphic. The algorithm works as well, as follows. You start by coloring the roots with the leaves, with the same color. The leaves are the nodes without any children. Then you go to the trees of height 1, which means that they are at distance 1 from a leaf. So here you can find that all the trees of height 1 have the same distribution of children, which are 2 green. So you can color them all of the same. And then you go one step further, and then you color them blue. Since on the left you have green, red, red, and on the right you have red, red, green. As I mentioned before, the trees are unordered, so the order of the children does not matter. And so, since the roots have received the same color, you can decide that the trees are isomorphic. Now I'll come back to the multiplicity of isomorphism. So let's try to see what happens on our problem, which is like, is there a simple substitution ciphering that goes from one tree to the other? So first, you know that in a tree isomorphism, the roots must be mapped together. So let's do that. Okay, so A goes with alpha. Now for the children of the roots, you have 2 options. The first B here on the left can either go to the beta on the left or the beta on the right. So you have 2 possibilities. So let's examine both. So here they are. Now you know that the other children, the other B, must go with the remaining beta. And now let's look at the children. So for instance, this A goes with this alpha, and this A goes with this gamma. Obviously, on the right instance, you can see that we have no longer have a bijection for the induced cipher, so this isomorphism does not induce a ciphering. But we can try to finish on the left one, and on the left one, everything works fine. So you can conclude that overall, there is one isomorphism that induces a cipher, which is correct. So the tree ciphering isomorphism problem can be stated as this. Sorry. Given 2 isomorphic unordered trees, is there any tree isomorphism that induces a cipher of the labels? And whereas the problem for messages was like very easy, actually this one is rather complicated. It has been proved under the name marked trees that this problem is graph isomorphism complete, which means that it is like believed to be more difficult than a polynomial problem, but less difficult than an NP complete. Actually, this class of complexity is unknown to be either in P or NP complete. I would like to show you how the reduction works for this. For this result, the proof is very easy. So you just take like a graph. A graph here is directed, but it works as well with undirected graphs. You take this graph, you number all the vertices from 1 to n, here 4, and then you start by creating a tree. The tree has a root with a label n+1 and n children numbered from 1 to n corresponding to the vertices of the graph. And then for each of these vertices, you will add children to them depending on which vertex they are connected to in the graph. So for instance, 1 in the graph is connected to 2 and 4. So you have 2 and 4 as children of 1, and 4 is connected to no node, so he has no children. Now, finding an isomorphism between the graphs is exactly equivalent as finding an isomorphism between the 2 trees that respect the labels on the distribution of labels on the trees, which is exactly the tree ciphering isomorphism problem. So obviously, our problem is not related to cryptography, but it was a nice way to introduce the problem. We are really interested in this problem as an isomorphism problem between trees. So this reduction is linear, obviously, so it's like a very cool property to investigate the graph isomorphism problem. Actually, all results we can deduce on the tree ciphering isomorphism problem can be as well hints for the graph isomorphism problem itself. So we stated earlier that there are many isomorphisms between 2 trees. And actually, the difficulty of the problem comes from that, because any isomorphism induces or not a ciphering, but the answer is quite obvious once you have the isomorphism. So the number of isomorphism is where the difficulty lies. Actually, the number of isomorphism between 2 trees depends only on their classes of equivalence. This number is expressed as product of factorial, because to obtain an isomorphic tree from one tree, you can just permute children that are of the same class, and this way you can obtain a new tree. And the number of isomorphism works exactly as the same. So the number of isomorphism is simply the product of all the permutation possible between children, sorry, that share the same class. And since they must be mapped, since the isomorphism must protect the parent-children relation, we can only restrict ourselves to see siblings that share the same class. So for instance, in this tree, the number of isomorphism is 8. But you can see when you generate round-up trees, even with small sizes such as 100, you can end up with like lots and lots of isomorphism. So the difficulty is indeed in this particular problem. So our strategy to solve the problem is as follows. We want to explicitly build the ciphering isomorphism if it exists. So the search space, as we just have seen, is all three isomorphism. So it's factorially large. So our goal in this paper and presentation, is to break the combinatorial complexity of the search space. Since we are actually building two bijections, one on the node, which is the tree isomorphism, and one on the labels, which is the ciphering on the labels, our main idea is to use the constraint of one bijection to make deduction about the other bijection and vice versa. So to illustrate what I mean by this, let's take an example. So those are two trees. They are isomorphic, and so let's try to illustrate the strategy. So first, you know that the isomorphism must map the roots. So here it goes. Now you know that B goes with beta. Now you look for the children of T1 and T2. So obviously you see that the C must go with the gamma, and you can also map C and gamma on the cipher. Now you cannot distinguish between the two A's, which one should go with the other alpha. But if you look like their children, you can see that here there is a beta, and a B and a beta, so they must be mapped together. Since they are mapped together, their parents must be mapped together, and you can now map those nodes. And now, just by deducing this A must go with this one, and this one with this one. And now you can see that with like simple deduction, you have almost completed the isomorphism. You have only two possibilities left, those C's with those gamma. And to complete the isomorphism, you can use, for instance, backtracking. And in this particular example, both choices would work. So this is our strategy. We are actually building in details the common denominator for the isomorphism that may lead to a ciphering. This means that we are trying to we will construct all the mandatory mappings between the nodes and the labels that all ciphering share. To do that, we will start with a big search space, bigger than the tree isomorphism one, and we will reduce this search space by applying filters, namely a filter on depth, parents, equivalence class, and labels. The idea is simply to state that, okay, so if two nodes are mapped together, they must share all the topology information, including their equivalence class, their depth, their height, their parents must be mapped together, they must have the label that are mapped together, and so on. So all these filters applied one after one will do this thing. So we start with the set of all bijection of the bijection between the nodes, and then at the end of the algorithm, we will have reduced the space to something which is maybe a little bigger than the tree ciphering set, because it's not guaranteed that at the end we have the complete isomorphism, but something which is actually smaller than the number of tree isomorphism. That is the goal of our algorithm. So now into details. First, we start by putting all nodes without considering any topology in something that I call a bag, which is an object that contains sets of nodes from T1 and T2 that are susceptible to be mapped together. So at first, all nodes are in the same bag. So any mapping between any nodes is accepted. And then we start with the first filter. The first filter is on depth. So depth is simply the distance of a node from the root. So since all map nodes must share the same depth, we split the bag by depth. So here you have the nodes of depth 0, the nodes of depth 1, and the nodes of depth 2. And now there is something important that happens with bags, is that if a bag contains only 2 elements, one node from T1 and one node from T2, since they are susceptible to be mapped together, they actually must be mapped together. So here, the bags of depth 0 contain only the roots, and so the roots are mapped together. This is very consistent with the definition of isomorphism. And the first step of depth filtering, we always map the roots together. Okay, now we can go on to the second filter. The second filter is based on the idea that if 2 nodes are mapped together, they must have the parents must be mapped together. So we will subdivide the bags between shared parents. So the first bag, nothing happens because they all share the same parent. But for the second bag, we split in 2 subsets depending on the parents. But actually, we don't know at this step which subset must go with each subset because we don't know how the parents must be mapped together. So we will compute what I call a children's signature, which is like the distribution of equivalent classes that can be obtained in linear time by the AU algorithm of each set. So here you have like green, red, red, and here everything is green and green. So here in this example, we cannot distinguish even further between those sets because they are the same signature. Obviously, it's an example. We cannot illustrate everything with an example, but this step is actually needed because if those sets were to differ, we could have deduced that they must have gone together. So since we cannot distinguish between them in this particular example, we simply remerge them, and in the end, we have not modified the bag at the end of this filter step in this example. Now we can partition the bag depending on the equivalence class. So here, this bag is split in 2 parts because you have the green one and the red one that go together. So we apply again the deduction rule on bags, and we can see that the C must go with the gamma, and we have mapped another nodes, and the ciphering increases. Okay, so now we have applied all topological filters. It remains only the labels. So for the labels, I use a concept that I call collections that are like sets of nodes that shares the same labels, and they are susceptible to form bags. Just as bags contain nodes that are susceptible to be mapped together, collection contains sets of nodes that are susceptible to form bags. It's like bag at the second order. So in this case, so the sets, the bag with only A's become a collection with 2 sets of A, and the collections here is formed of several subsets. And as for bags where there is a deduction rule, there are deduction rules for the collection. The first deduction rule is that whenever a collection contains sets of same cardinality, and the label of those sets are already mapped, then you can put them into a bag. So for instance, here B and beta are already mapped, C and gamma as well. So you know that this beta must go with this B and this gamma with this C. So you extract them from the collection to form a new bag. So now the collections left only contains labels that are never been seen. And now the second deduction rule is that when a collection contains 2 sets of same cardinality, but only 2 sets, then they also must form a bag and their labels should be mapped. So here it means that those A and alpha must be mapped together, and those A and alpha must be mapped, put to a bag together. Sorry. So you end up with these bags. At distance, you can see that all the collection has been like totally removed because we managed to put everyone into a bag, but it's not mandatory. And it can happen, depending on the trees you consider, that even at the end of these steps, you still have collections because you were unable to make enough deductions. And now we can apply the deductions on bags just as before. So those B must go together. Since we have mapped those nodes, their parents must be mapped together as well. We split the bag here, and now we can apply deduction rule once again. And now we are finished. We cannot go any further on mandatory deductions, and we can finish building the isomorphism by backtracking. And you must have recognized the figure that I illustrated before, but now this has been obtained by like a proper algorithm. So how does this algorithm works in practice, like from the complexity point of view? Obviously, the number of map nodes is bounded by the size of the trees. You cannot map more nodes than there are present in the trees. But each mapping has a variable cost, because depending on whether the parents are mapped or not, depending on whether the mapping will split a bag or not, you will make a variable number of deductions. And so you cannot know in advance the cost for a mapping. But it seems that when repeated on sufficiently that on many nodes, the cost is amortized, and you can see on the figure on the left that globally the algorithms behave as a linear, which is a good property. It seems that the time does not depend on the size of the alphabet, which is the number of different labels, and increase linearly with the size of the tree. In this case, the trees are isomorphic, so everything went fine. Obviously, in all that I described earlier, if at some point something went bad, like you don't have a bijection at some point, you know that you cannot have a ciphering, meaning that the sets of ciphering is empty, and you can conclude immediately that there is no ciphering. So in this example, in this figure, the red triangles are the mean time for the previous case, and here you can see that you are able to conclude negatively to the question of is there a ciphering in a sublinear time, which is also a good property. Also, we claimed earlier that the goal of the algorithm is to break down the combinatorial complexity. So to assess that, I introduce the ratio R, which is simply the log 10 of the ratio between the size of the search space and the number of tree isomorphism between T1 and T2. So our goal is that this ratio is below 0, meaning that the search space remaining is actually lower than the initial search space of tree isomorphism. So if you remember in the example, when we started, all nodes were susceptible to be mapped together and they were in a single bag. So obviously, these 8 factorial possibilities of mappings is far bigger than the number of tree isomorphisms. So we start largely above 0. And after the first filter, where we mapped the roots and subdivide the bag, we have like a smaller value, but still superior at 0. The depth of parent didn't change anything on the bag, so this number does not change. After applying equivalence classes, we managed to map C with gamma, and so the ratio decreased a little bit. And after the labels and the deduction on collection and so on, we arrive with only like 2 possibilities here. And so now at the end of the algorithm, the ratio is indeed negative as hoped. Actually, if we repeat this experiment on different trees, you can see that on the left here, for tree of size 100 and an alphabet size of 5, you can see that the algorithm always managed to reduce the search space below the search space of isomorphism at the end of all steps. And if you take, and in a sense, you can see that even the steps that were not useful in our previous example are here needed and useful to reduce the size of the space. If you take a closer look at the final R after the end of the algorithm, we can see that despite some pathological cases for some very small trees, the algorithm always managed to reduce the search space, and it seems that the factor of reduction grows linearly in log 10, so exponentially, on the size of the trees. So on average, the search space is reduced by an exponential factor, which is a very good property. So as a recap, for the tree ciphering isomorphism, we develop an algorithm that does not solve entirely the problem. You still have the backtracking part at the end, but this pre-processing part, in some sort, runs in linear time in practice and reduces the search space by an exponential factor on average. So given the low computational cost, this algorithm is actually pretty good for like to solve the problem. After that, we can end up with backtracking. So I have some results on backtracking, but they are not in the paper. So I will present to them like in the real live presentation in a few weeks. And you can, in the meantime, find all the details with the proper formalism in the paper. I thank you all for listening, and I wish you all to see you at the conference. Bye.